Welcome to this last part of the tutorial on designing distributed software in mCRL2. We previously saw how we can model processes in mCRL2 using process algebra and data, and how we can express properties using the modal mu calculus. And in fact, we ended our previous part with the observation that this naive mutual exclusion algorithm satisfies mutual exclusion, but it's not the case that every process can always eventually request access to its critical section. So if we remember correctly here, the reason for that was that if both processes immediately set their flag to true, they end up waiting for each other. So apparently there is some sort of tie between the two processes that we now need to break in order to satisfy this property. In this last part of the tutorial, we will present two mutual exclusion algorithms that address this problem in different ways. The first algorithm is Dekker's algorithm. And the way Dekker's algorithm addresses this tie is that it introduces a turn variable that gives priority to one of the two processes. So if both processes have set their flag, then one of the processes gets priority over the other and is allowed to enter the critical section. And it achieves this as follows. If the flag of the other process is true, then process I will check if it has priority. If it has priority, the turn is equal to I. So if process I does not have priority, then it will temporarily set its flag to false, allowing the other process to break from the loop and enter its critical section. And it will then wait until the flag of the other process becomes false. The only reason for the flag of the other process to become false is because that leaves the critical section. Now, once the flag of the other process becomes false, this process sets the flag to true. And hopefully, once it then checks the condition here, the flag of the other process is still false, and process I can break from the loop and enter the critical section. Now, the question is, first, how do we model this? So previously, we saw only how we can model a busy waiting loop. And now we actually need to do work inside this loop. So the first question is, how do we model this in mCRL2? Well, in order to model this, we split the algorithm into two parts. The first part, where the flag is set to true, essentially the entry into the loop, and the loop itself and everything that's executed after the loop. The reason we do that is because at the end of one iteration of the loop, we need to be able to jump back to the beginning of the loop. Now, the loop is modeled as follows. We first read the shared variable and temporarily store that in a local variable flag other. And for that, we use this sum here. Then we check the condition. If the flag of the other process is true, then we need to enter the loop and execute its body. If not, we jump to the end of the loop, so we set the turn and enter the critical section and set the flag to false. Modeling this is exactly similar to what we saw in the previous algorithms. So let's focus on the body of the loop. For the body of the loop, again, we have a condition in the if here, for which we need the value of a shared variable. So we read the shared variable here, turn, and store its value in a local variable turn, and then check the condition. If turn is not equal to I, so the condition of the if holds here, we need to enter the body. So similar to what we modeled before, we set the flag to false, model this busy waiting loop, waiting until the flag of the other process becomes false, and then finally set the flag to true. And then we repeat, so we jump back to the beginning of the loop, and we can recheck the condition. If the condition is false, so else, we skip over the if and we immediately return to the beginning of the loop. So this way we can model Dekker's algorithm. Now remember that we extended the set flag action. So we now have two places where we set the flag action. So it's not that evident anymore that setting the flag corresponds to expressing the wish to enter the critical section. Therefore, for the sake of modeling and verification, we extend the first set flag to a multi-action where we include that process I wishes to enter its critical section. And we update the property accordingly. So we can now verify this property in mCRL2 IDE, and indeed this property holds. So indeed the changes that were made in Dekker's algorithm address this property, and we can now always eventually request access to the critical section. Now, a next logical question is then, once a process wishes access to its critical section, will it get access to it? So this can be expressed using this formula here, where we say that always, whenever a process wishes access to its critical section, then this property holds. Now, this property is a least fixed point, which means that we can, for the property to hold, we can only recurse through x finitely many times. And the property says that in x, well, every path which only goes through actions that are not enter I, well, they recurse through x again. So all paths where we do not execute enter I are finite for this property to hold. And that means that every path of such actions, so not enter I actions, end up in a state where the only thing we can do is enter I, or possibly it's a deadlock state. However, deadlock states are excluded here by this diamond true. Now let's see if this property is satisfied by Dekker's algorithm. So this eventual access property that I list here is exactly the property that I showed on the slide. And if we verify that property, we get a counterexample. We could, of course, visualize the counterexample again in LTS graph, but for the sake of understanding what's going on, I include it here on the slide. In the algorithm to the left here, the red arrow indicates the position of process 0, and the blue arrow indicates the position of process 1. And we can now follow the counterexample. So first, process 0 sets the flag to true. Then it gets the flag of process 1, which is false. So the guard of the loop is false, and it skips the loop. And it sets the turn to process 1. Now process 1 comes and sets its flag to true and gets the flag of process 0, which is true, so process 1 must now enter the body of the loop. And it then checks whether it has priority or not. Well, it has priority, so it should not set the flag to false. So it jumps over the if, and now it keeps doing so. So what we see here is a typical fairness issue where apparently process 1 gets all CPU time, and process 0, although it is ready to enter its critical section, is not allowed to make any progress. We could modify this property and exclude such fair paths, and that is what we describe in the paper. However, here instead I will switch the attention to Peterson's algorithm, which by itself does not allow these kinds of unfair executions, as we'll see. So Peterson's algorithm deals with breaking this tie in a slightly different way. And what it does is the following. If it sets its flag to true, it will behave in a more gentlemanly way and it will say, well, the other process can go first. And then it waits as long as both the flag of the other process is true and the turn was set in such a way that the other process can go first. In fact, this says that both processes had set its flag, and this process was the last to set a value for turn, so the other process can go first. And once one of these two conditions becomes false, this process will enter its critical section. And if we then verify eventual access, indeed, this property is satisfied by Peterson's algorithm. So that's nice. When Peterson's algorithm requests access to the critical section, it's guaranteed that it gets access to the critical section in some finite number of steps. Now, a natural question is, how many times, if process 0 requests access to the critical section, how many times can process 1 enter its critical section before process 0 enters? And this is, in a sense, an adaptation of the property that we had before. This is a slightly stricter requirement. And we can say that process 1 can enter b times before process 0 enters. And we do that as follows. We say that always whenever process I wishes to enter its critical section, then we start counting the number of times the other process enters. And we do that by keeping track of this number of times in the parameter of this fixed point. And how do we keep track of that? Well, first of all, in every step, we check whether the bound is still, whether the number of times the process entered is still less than or equal to b. And if the other process enters, then we increment the value n. And for any action other than an enter action, this n just stays the same. So in fact, this means that when we do just an enter action, then we just need to check this one condition here. Now, let's see what happens if we verify this, this property of Peterson's algorithm. So it's bounded overtaking, and we set the bound to 1. So this is exactly the formula that I showed on the slide, where the bound is set to 1. And if we verify this property, then we get this counterexample. Now let's understand the counterexample. Let's optimize the layout a bit. Let's untangle. And the counterexample now is as follows. First, process 1 wishes to enter its critical section, sets the turn to 0, and gets the flag of process 0, which is false. So at this point, process 1 can enter its critical section. Then process 0 comes and expresses the wish to enter the critical section. Then process 1 enters, leaves, sets its flag to false, and immediately after that, process 1 requests access to the critical section again. So at this point, process 1 has entered once. But also observe that process 0 only set its flag and did not yet set the turn to 1. Now first, process 1 sets the turn to 0, and then process 0 takes a step and sets the turn to 1. So here, process 0 gives priority to process 1, and process 1 observes that it's its own turn, and it enters the critical section. So here, process 1 entered twice after the point where process 0 set its flag to true, and clearly bounded overtaking is not satisfied for 1. Now, if we look more closely here, after entering, well, if process 1 leaves the critical section, sets its flag to false, and it would try to pull this trick off again, the turn would end up being set to 1. And at that point, process 1 cannot enter the critical section before process 0 has entered. So at this point, process 0 is forced to make progress into its critical section. So this suggests that bounded overtaking with bound 2 is satisfied. So let's just check whether that is indeed the case, and yes, this property holds. So that's nice. This means that Peterson's algorithm satisfies mutual exclusion, can always eventually request access to the critical section. It satisfies eventual access, but it also satisfies the stronger property of bounded overtaking. So that means that basically we have now successfully verified Peterson's algorithm, and it satisfies all the desired properties for a mutual exclusion algorithm. Now, to wrap up this tutorial, I would like to share one anecdote, and that is the following. Sometime in 2015, so roughly 6 years ago, Peterson's algorithm on Wikipedia was described, well, just as we described it in the presentation today, but the initialization was changed slightly. In the initialization, the flag of process 1 was initially set to true, and the flag of process 0 was set to false. So basically, this means that the flag is set in such a way that process 1 has already requested access to the critical section. Now we can wonder, does this in any way affect the correctness of the algorithm? And it turns out that if we verify this, all of the properties that we verified so far still hold. But there is a clear and crucial difference between these two algorithms. So if we look at this initialization, think about what happens if now process 1 wants access to its critical section. So it sets the flag to true, it sets the turn to 1, and then it checks this condition. So remember, process 1 has not done anything. In particular, process 1 is not ready to enter its critical section. However, the turn is set to 1 because process 0 just set it to it. But because of the initialization, also the flag is true. So that means that in order to enter its critical section, process 0 needs the cooperation of process 1. Because process 1 needs to set its flag to true, well, that will not change anything, but also it needs to set the turn to 0, and only after process 1 has set the turn to 0, process 0 can enter its critical section. Now, of course, this is an undesired situation, and we can check for it with a modal mu calculus formula. So this formula is a bit more elaborate, and it checks, well, it keeps track of the number of processes that has requested access to its critical section, but has not yet left the critical section. So we keep track of that in this parameter n. Whenever a process requests access to the critical section, we increment n. Whenever it leaves the critical section, we decrement. And for any other step, the value of n just stays the same. Now, whenever the value is 0, so that means no process has requested access to the critical section, We would like a process that requests access to its critical section to be able to enter the critical section without cooperation of the other process. So that means here that we should be able to do an enter action without seeing a wish to enter the critical section or an enter into the critical section of the other process. This is, in essence, an adaptation of the eventual access property. And if we verify this, then we see that this property is not satisfied for the version where the flag of process 1 is initialized to true, and it is satisfied for the algorithm where the flag is initialized to false. So this way, we actually uncovered a bug in the version of Peterson's algorithm as it was described on Wikipedia 6 years ago. And with that, we have come to the end of this tutorial. More information about mCRL2 is available from the homepage, and that includes all the models that were used in this tutorial. Background reading is the book Modeling and Analysis of Communicating Systems. And if you would like to dive more into the theory and into the applications of mCRL2, I refer you to the Coursera courses. Links to the courses are also available from the mCRL2 homepage. And with that, I would like to thank you also on behalf of Jan Frieso Grote.